My name is Dr. Saavan Patel. I'm CTO of InfinityQ Technologies. I'm excited to share our exciting plan and our company with you. So I don't need to tell everyone here about the importance of hard optimization problems. These exist in the world around us on varying time scales in every kind of industry. From finance, doing kind of trading and algorithmic portfolio optimization, to logistics, routing packages, scheduling, to life sciences, doing protein folding and molecular discovery. The important thing is that when we've talked to leaders in each of these industries, is they all realize they're leaving performance on the table. They know that they're not getting the best solution. They are waiting for hours for their solution anyways, but we think that we can bring quantum to them in a meaningful way through our optimization platforms. So, what does this look like? Of course, quantum computing is the future, and that's why we're all here. The problem, of course, is that in the NISQ era, and as we heard this morning in the keynote, it's very hard for these quantum computers to get past 100 qubits. And not for a number of years will this be possible. So we're left with what we have, which is digital computing, shown on the right here. Of course, this is what we use every day, but the representational power of a digital computer is not really where it needs to be to solve these hard problems. You're stuck in a 0 or a 1. What is in the middle? And this is where we think InfinityQ can add value in our probabilistic computing simulations. It's systems. These probabilistic computing systems are based on 5 years of my own work at Berkeley, as well as foundational work at UC Santa Barbara and Purdue, where we've built up these systems using our own kind of hardware accelerators. So we have one of the largest Ising machines available on the market. In fact, as far as I know, it is the largest fully connected Ising machine available at 144,000 nodes and available on a single GPU system. This is a large and flexible system that you can access through our web API right now. Our slogan, of course, is bigger, faster, and greener. This is the real value that we bring to our customers. Bigger, we can solve very large systems. As I said, 144,000 nodes is the largest we're at. Faster, we're about up to 1,000 times faster than the classical competitors that we're going up against. And greener. Greener comes in a few forms. It means that we use less energy on our computations because we're so much faster and using specialized hardware. But it also means every mile that we take off the road for the delivery drivers that we're optimizing for is fewer greenhouse gases in the air. And we're delivering all of these right now. But 1,000x faster is a big ask, and you might tell me that's kind of ridiculous. Where is this number coming from? Well, what we found is that compared to the fastest general purpose classical optimizer, this is Gurobi, we're 800 times faster on a 10,000 node max cut benchmark problem. The interesting thing is, while also being 800 times faster, we also produce a 1.5% better solution in less time. When we scale up the larger systems, Gurobi just crashes on us. So we can solve larger problems and we can solve them faster. And as I was mentioning before, what is the other competition in the Ising machine space? So the main ones are folks out of Toshiba and Fujitsu. And we're able to be right up against their heels in a single GPU configuration where they're using multiple GPUs, reducing our cost while delivering similar performance and speed. And of course, this is all theoretical. What is a practical thing that we've done for a potential customer? A client came to us with a grid optimization problem. They said, we want to solve, minimize our total costs, maximize our green energy production while respecting a set of constraints of maximum and minimum power for our plants and a set of other cross constraints. What we're able to build for them is a proof of concept where we solve the 50,000 provider problem for them in under 100 milliseconds, which enables real-time grid optimization for this customer. Another example, we've built out a last mile delivery solution, a last mile delivery API, which is shown on the right here. This is an actual screenshot from our web framework. We can deliver 10,000 parcels and route optimize this in under 3 minutes. This gives the folks that we're building these solutions for the ability to rerun as many times as they want every morning. Of course, this reduces carbon footprint and provides additional revenue for both the customers and ourselves. Last application space is life sciences. We've partnered with McGill University to solve faster molecular dynamics simulations, enabling better drug discovery and new chemical compounds. And to build out our ecosystem traction, we've partnered with Strangeworks, where you can get access to our API right now. This enables us to target larger clients through like Deloitte, Amazon, and J&J. Our go-to-market is a POC-driven system where, I tell my customers all the time, look, just let us solve your problem. We can show you what we're capable of. And then we build that out for them and have a SaaS model going forward after that. And it's nothing without the team. Our CEO, Aurélie Heloui, has 20 years of multidisciplinary experience in engineering, as well as she was a senior French Navy officer. I completed my PhD at Berkeley, where I did 6 years of this work in probabilistic computing. And then we have a world-class team of technical and strategic advisors. And that's what I got. Open to any questions.
Thank you.
I realized it was very rapid fire, but hopefully you got the gist of it.
Is this on? Hi, thank you for the presentation. I was wondering, how do you balance the two approaches, the two, domains in your approach? When is it problem dependent, or do you have a sort of a general approach where you integrate the two and then you build on that? Just if you could dig a little more into it.
You mean quantum and classical
quantum
computing?
And the classical,
yeah.
Yes.
So our thesis kind of is that quantum computers have really interesting mathematics that work very well. The issue is that the underlying hardware doesn't necessarily work the best way. So what we like to do is take the interesting mathematical pieces and then put it onto specialized classical hardware. So you have this nice mix of the both worlds.
Yeah, so can you tell me a little bit more about what this is going to look like when you get into the self-service side of it? What are you taking off your own back that your customers are going to do for themselves?
Sorry, I missed the first part.
This self-service component of this, you said you go from POC to self-service.
Okay.
So just I'd like to understand what that looks like in the future.
Yeah, so maybe I could give you a concrete example. So when we've done a POC, this is for a large logistics provider. They gave us a problem, and we realized that there were certain things that they would like to have in our solver that we didn't currently have. Through this POC, we built out additional solver features for them, but then we integrated that back into our SaaS model, so it'll be generally available for any other future customers that come. And then we built out a slightly customized or differentiated front end for them. So we still maintain all of our IP, and everything that we build for our customers through this POC, we resell every time, and they are billed on a per solve basis. Thanks.